So this video is about limits. Just the idea of limits, how we define them, when they exist and when they don't. So if we're looking at a graph, which is the easiest way to kind of understand a limit, then we say let f be a function on the interval from a to b. Okay, so we're just talking about some function, a function. Remember what a function is. Inputs, outputs, for every input there's one and only one output. And somewhere in here is this point C. We say at C, let's look at the limit. Okay, and the reason we want to talk about limits is sometimes it's got a hole in it at C, and that can happen. So let's say C is somewhere between 1 and 2, and let's say that is 2. So we can't really say that, for instance, f of c is 2, right? That we can put in the c and get out 2. We can't really say that we can do that. So that's where we start to talk about limits, okay? If I put in values slightly to the right of c, c in like 0.00001, just a little bit more, I'm going to get a number that's just slightly bigger than 2. And same as over here, if I put it just to the left of c, I'm going to get numbers that are just a little bit less than 2. But as I put numbers into the function, on the left of c and on the right of c, I'm going to get numbers that are really getting closer and closer and closer to 2. It's approaching 2 from the right, it's approaching 2 from the left. Okay, and I can get pretty much as close to 2 as you want me to get. If it's not close enough, I'll get a little bit closer to c, and I'll get you a little bit closer to 2. Okay? So that is what a limit is. If I keep coming from the right and from the left, I'm approaching the same number, the number 2 in this case, then let's call this function f. I don't know why I started writing that. Function f. We'd say the limit as x approaches c of f of x is 2, right? And I think you can see that fairly well, that as I come close to c on the left and the right, the limit is 2. The thing that you start to ask yourself now is, well, that's simple. When doesn't a limit exist? Here's a simple example of when a limit doesn't exist, using a picture again. Okay? The very basic part of it is that from the left and the right, they approach the same number. So if this is my function, this is very simple to see that there's no limit here at this point. Here there is, and here there is lots everywhere else, but right here, right? If this is c, then there's no limit at c. The limit doesn't exist. We say it doesn't exist because the graph is discontinuous at c, and you can see that that word discontinuous must mean that it doesn't break up like this, but it does break up. So here it's approaching, like, I don't know, 4, and here on the left is approaching 2, and those two numbers are not getting close to each other like this guy up here did. They got really close to each other, but on this other one, they're not. Okay, so that's one time when a limit would not exist. And that's the basic idea of what a limit is. So another example of when a limit does not exist is, let's say that there's this this function here. Okay, I think 1 over x squared would produce a graph like this. Does the limit exist at 0? What's the limit as x approaches 0 of 1 over x squared? As we get closer and closer and closer to 0 from the left and the right, one number, one single value is it approaching? It doesn't. It just keeps getting bigger. If I put in, a number that's really close to 0 right here, then I'm just going to get this really small number. 1 divided by this really small number is a really big number. So it's just going to keep producing larger and larger numbers, and this doesn't approach one single value. So there is no limit, okay? The limit does not exist because we say the function is unbounded. There's no bound. It just keeps going forever and ever and ever. All right? So there's another reason a limit might not exist. Just one last one, just because it's pretty cool. We say y equals the sine of 1 over x. Okay? And we're going to talk about at 0. Okay? Let's just think about this without drawing the graph even. What's going to happen around 0? Let's just look at this guy right here, 1 over x. As I put numbers that are really close to 0 into 1 over x, I get, 1 over something that's close to 0, a really small number. And 1 over a small number is a big number. Okay, so I'm going to get increasingly large numbers in here as I get closer and closer to 0. So as I get larger and larger numbers, what happens when I take the sign of this large number? Well, let's remember our unit circles. Okay. For any angle, theta, that I find in here, the sine is just going to be, the y component of this point on the circle. Right, this is the cosine, this is the sine, this is like maybe 45 degrees, so the sine of this theta would be the square root of 2 over 2, just a guess. And I could take this theta, and it's going to be something, and this theta, it's going to be something, and something, and something. All of these thetas, I can find a sine associated with all of them. But we're talking about a big number here. What happens when I get a big number, and I want to find the sine? Well, okay, a big number. So that means I go around, this is 2 pi, or 360 degrees, and I go around it again. And, a big number is a big angle for sine. The bigger the angle I get, what difference does it make? It doesn't make any difference. Here, I'll stop here, let's say. And so if I stop there, what's the sine? Is it really big? No, the sine is always going to be between positive 1 and down here is negative 1. Remember that from the unit circle. So no matter how big an angle I put in here, I'm just going to get out some number that's between negative 1 and 1. Okay? So as I keep getting closer to 0, right, small number, putting in small numbers for x, getting close to 0, I just get out increasingly big numbers. And it's, as I put in these big numbers to sine, it's almost just like giving it some random angle, asking it what the sine is, it tells you, but it doesn't approach a single value, right? And if you were to graph it and zoom in on it, you're going to see, like, here's 1. Way out there is 1. Let's say this is, right here is 0.1. We're really zoomed in here, okay? So, say for 1 divided by 0.1 is 0.1. Okay, so, sorry, 1 divided by 0.1, right? We're putting in a 0.1 for x. 1 divided by 0.1 is going to be 10, and 10 is something like, let's say it's something negative, I'm thinking. See, this is 3, yeah, something negative. It's hard to say. I'm not sure exactly, but somewhere around here, it's negative something, and getting smaller, getting closer to negative 1, and then it's gonna come back up, and it's gonna hit 1 eventually, and then it's gonna come back down, and it's just going to do these crazy oscillations, and the closer you get, the more oscillations you're going to see near 0, and it never, crosses right there. Just the closer you get to 0, the crazier it gets, the more oscillations you're going to see in a shorter span. And so since it doesn't approach any value on the right, and it would do the same thing on the left, it wouldn't approach any value on the left, there's no limit. We say the limit doesn't exist because of infinite oscillations. That's right, I think. Pretty sure about that. Infinite oscillations cause the limit not to exist. Okay, so that's just a quick overview of graphically the idea of what a limit is, just so you can get just wrap your head around it.